Welcome to this domains video, in which we will be looking at how to set up circuits to produce results showing the relationship between the current in a component and the potential difference across it. We will look at how to plot graphs of these results and to interpret them. Graphs showing the relationship between current and potential difference are often called characteristic curves, as they have distinctive shapes for the type of component tested. In making this video, John and I have used some extracts from videos we made for teachers to use while practical work wasn't possible due to COVID restrictions. The full versions of these videos, together with teachers' notes, are available by following the links shown. We know that not everyone will want or need to watch the whole of this video, and the next slide shows approximate timings of each section of the video so that you can skip through to the parts that you would want to see.
Rather than simply giving students the circuit, it can help to consolidate their understanding if we encourage them to think about how to plan the experiment themselves in order to get the results they need. For example, what components do we need in the circuit? Well, to start with, we need the component we're going to test, which we'll call for the moment X. We'll need a complete conducting loop for the charges to flow round, and a power supply to cause those charges to move. We'll need an ammeter to measure the rate of flow of charge, in other words, the current, and we'll need a voltmeter to measure the potential difference across the component. As it stands, this circuit is exactly the same as the one you would use in calorimetry experiments to measure, say, the specific heat capacity of water or aluminium. The only difference is that X would be the immersion heater. But in this case, we need to achieve a range of potential differences and currents. So we need a means of altering that, which is where we have a variable resistor. Some schools have power supplies that are continuously variable. In other words, the potential difference can, in theory, be set to any value within the available range. The advantages of these are that they're easy to use, but they are expensive, and fine control of potential difference may be difficult, so use of a variable resistor may be necessary. Exam boards don't always consider them to be an alternative to using variable resistors, and a number of exam questions will show circuits which have the variable resistors in them. Alternatively, many schools have access to switchable potential difference power supplies. The only difference with these is that the potential difference is only variable in steps, and these steps do not necessarily correspond to exact values of potential difference that we want. To enable the potential differences to be set to precise values, a variable resistor or rheostat is used, usually in series with the power supply. In addition, the values of potential difference labelled on any type of power supply are often significantly different to the actual potential difference produced. If no power supplies are available, the experiment is still possible using battery packs, provided they allow you to connect 1, 2, 3, and maybe 4 cells in series, so it effectively acts like a switchable power supply in 1.5 volt steps. A typical laboratory ammeter displays current values rounded to the nearest 0.01 amps. The effect of this rounding means that all readings are subject to an uncertainty of plus or minus 0.005 amps. While this may seem very small, it is significant if we are only measuring currents below 0.1 amp. We need therefore to choose our circuit components carefully in order to achieve a range of currents that go up to at least 0.5 of an amp. That's 100 times the uncertainty. The same principle applies to voltmeter readings. Variable resistors, also known as rheostats, are used to provide fine control of potential difference and current in a circuit. When choosing one for use in a circuit, firstly, it must be able to take currents above the expected maximum in the investigation. The ones on the left use a coil of resistance wire and are generally capable of taking a current of several amps. The one on the right uses a carbon track and is only suitable for small currents, typically much less than 1 amp. Secondly, the maximum value of the variable resistance should be in the same approximate range as the component being investigated. If this maximum value is too high, then all readings would need to be taken in the first few millimeters at the low resistance end of the coil, making precise setting of potential difference and current very difficult. If, however, this maximum value is too low, then the variable resistor would have very little effect on the potential difference and current, making it impossible to achieve a reasonable range of results. The variable resistor used in the video you'll see shortly has a stated resistance range of 0 to 6.8 ohms and a maximum current of 5 amps. Finally, it is important to be aware that current has a heating effect and that components in the circuit, particularly the one being investigated and the rheostat, may get too hot to touch when the current is near the maximum value for the range. Whilst this is not usually dangerous, a warning to students would be in order.
The starting point for graphs is for students to determine which way round their axes go. For this particular case, the potential difference is the independent variable, and we would normally put that on the x-axis. The current is the dependent variable, and therefore that should go on the y-axis. Most exam questions will actually ask for current against potential difference, and this wording needs to be explicit for the students.
The first component we will investigate is a resistor. The ideal resistors to use for this are in the form of a metallic wire-wound resistor encased in a brass or ceramic casing and with a power rating of at least 5 watts. Now the reasons for this are, firstly, it allows us to relate the results to Ohm's law, which states that the potential difference across a metallic conductor at constant temperature is proportional to the current in it. Secondly, resistance values from 5 ohms to 25 ohms allows us to use a suitable range of potential differences and currents. A 23 ohm resistor was used to make the video clip you'll see shortly. Standard resistors, like the electronic one at the bottom, are not suitable. They are based around a piece of carbon and tend to have a power rating in the region of 0.25 watts. In practice, this means that, for example, a 10 ohm resistor would start to seriously overheat once a current of 0.16 amps had been exceeded. This therefore significantly reduces the range of currents available, and the risk of irreversible damage to the resistors is high. The circuit is initially set up without the voltmeter because it encourages students to adopt a methodical approach to setting up circuits by following a loop from the positive to the negative terminals of the power supply. In practice, it helps students to avoid confusing the ammeter with the voltmeter, and it allows us to check there are no breaks in the circuit. If there are no breaks, the ammeter should produce a non-zero reading when the power supply is turned on. A word of warning here. Make sure the power supply is at a low but non-zero setting. A poorly set up circuit may have a short circuit, allowing a large current to flow. Ammeters can be damaged or internal fuses in them blown if their maximum current is exceeded. With the power supply initially set to 0, the potential difference is then increased in 1 volt increments from 0 up to, in this case, 6 volts. Precise values of potential difference are very difficult to achieve, and values of both potential difference and current fluctuate. This can provide useful evidence to support discussions about reliability of results and how best to cope with the fluctuations. If your exam board requires students to know about and plot results for current in the reverse direction, the easiest way to achieve the results is by reversing the connections to the power supply. As mentioned before, during the experiment, the resistor will get hot. Ideally, and to conform fully with Ohm's law, the power supply should be turned off and the resistor allowed to cool between readings. Resistors such as these, however, are made of a material where the resistance changes very little with temperature, so not allowing any cooling time has no noticeable effect on the results.
A graph of current against potential difference for a resistor at constant temperature should be a straight line through the origin. Students need to recognise that any straight line through the origin means that the variables on the two axes are directly proportional to one another. In this case, the current is directly proportional to the potential difference across the resistor. Resistance can be calculated using R equals B divided by I, and this can be done for any point on that line. But the easiest way is to use the gradient. The gradient of the line, however, would give a value of I divided by V, and therefore the resistance would actually have to be 1 divided by the gradient. And this is something that sometimes confuses the students because they have a graph where the higher the resistance, the lower the gradient.
To investigate a filament lamp, we simply put the lamp in the circuit in place of the resistor. The choice of the lamp is, however, quite important. Low voltage, low power lamps used in lower school experiments may not allow an adequate range of currents and potential differences to be covered. They can easily be overloaded, so are best used with batteries or power supplies, where the maximum potential difference can be locked. In my experience, they do not always produce the shape of graph expected, but I know some colleagues have used them successfully. If you are using a power supply, 12-volt lamps rated at between 15 watts and 36 watts are suitable over a range of potential differences from 0 to 10 or 12 volts. In the past, I've actually used ray boxes for this purpose, although they have to be the ones with filament lamps, not the LED type. As before, we suggest initially setting up the circuit without the voltmeter. Once we know the circuit is working, the voltmeter can be connected across the lamp. It is worth checking at this point that the lamp will glow when the current is increased. With the power supply initially set to 0, the potential difference is then increased in 1 volt increments from 0 up to, in this case, 10 volts. Precise values of potential difference are very difficult to achieve, and values of both potential difference and current fluctuate. This can provide useful evidence to support discussions about reliability of results and how best to cope with the fluctuations. During the experiment, students should make a note of the colour and brightness of the bulb, as this relates to the temperature. When the filament is glowing white hot, its temperature could well be between 1500 and 2000 degrees C. If your exam board requires students to know about and plot graphs for current in the reverse direction, the easiest way to achieve these results is by reversing connections to the power supply.
An example of a correctly drawn graph is shown. For students to interpret this, they need to be clear about some of the key features that the graph is showing. First of all, that the graph does actually go through the origin, so therefore there is a zero current when the potential difference is 0. Secondly, they should see that the gradient of the graph is actually getting less at higher values of potential difference. This should indicate to them that the resistance of the filament lamp is increasing as the potential difference and the current increase. They could take two values from the graph to actually calculate what that resistance is. The first point is shown at a potential difference of 1.5 volts and a current of 1 amp. They should then work out that the resistance is the potential difference divided by the current, 1.5 divided by 1, and they will get a resistance of 1.5 ohms. Then look at the second point. You have a potential difference of 4 volts and a current of 2 amps, and therefore they would have a resistance of 4 divided by 2, which is 2 ohms. There are two clear values showing that the resistance has increased between those 2 points from 1.5 ohms to 2 ohms. They then need to think about how they could answer a question. Many questions use the command words, describe and explain. Describe is what they should be able to say they are seeing. Explain is the why. For the students to be able to explain why the resistance of a filament lamp increases with increasing potential difference across it, they need to already have a clear model for the structure of the metal filament. The ions in the lattice are always vibrating, and there are delocalized electrons free to move about this lattice. As the potential difference increases, there is more work done per unit charge, which they could use the equation V equals W over Q, and the free electrons will move faster. This means that the current increases, because current is the rate of flow of charge. The rate of collisions between the free electrons and the ions increases. Energy transfers to the ionic lattice, causing the amplitude of the ion vibrations to increase. This means that the filament temperature is increasing and that there is more resistance to current flow. If students have plotted potential difference against current instead, then it is still possible for their graph to be correct, but it would obviously need to be curving in the opposite direction. Here you can see two graphs that your students might draw. The graph on the left has an unclear line shape, which may have been caused by the student not having a sharp pencil and not using an eraser. The intercept with the origin is unclear, and the student needs to appreciate why the line would pass through the origin. and that there would be no current flow when the potential difference is zero. The graph to the right shows a mistake more commonly seen. The change in the curvature at both ends of the line is incorrect. They are showing a decrease in current for an increase in potential difference, and this would not occur.
The best diodes to use for these investigations are those classified as rectifier diodes, and they should be capable of carrying currents of at least 0.5 amps and preferably 1 amp. Suitable diodes are shown in the diagram here, and as you can see, they're not enormously expensive. Diodes have a very interesting property, however, in that they have almost no resistance to current in one direction and almost infinite resistance to current in the opposite direction. It is therefore very useful to have the diode mounted on a base that shows its orientation in the circuit. Due to a diode having virtually no resistance to current in the one direction, it is essential to include a protective resistor in series with the diode to avoid excessive currents that would damage it. A 10 ohm resistor is suitable. As before, we recommend a systematic approach to setting up the circuit, working from the positive of the power supply round to the negative. In particular, this is important to ensure that the protective resistor goes in the correct place in the circuit. It's particularly important to ensure that the voltmeter is connected across the diode and not the protective resistor. The experiment proceeds with the power supply initially being set to 0, and then the power supply and rheostat being used to vary the potential difference and current through the diode. However, it soon becomes apparent that 1 volt increments in potential difference are impossible. Students could at this point be asked to consider how best to proceed once they realise that increasing the potential difference in 1 volt increments is not possible. In this case, perhaps the best approach is for the current to become the independent variable. During the experiment, students should note the potential difference at which the current first starts to flow, as well as the values of potential difference at each value of current. More able groups could be invited to investigate more closely the relationship between the current and the potential difference for potential differences between 0 and 0.6 volts. Fluctuations in the readings are unavoidable and can be used to prompt discussion about how best to cope with them and the reliability of the measurements. The experiment continues with the connections to the power supply being reversed to obtain results for current in the reverse direction. Students should soon realise that there is no detectable current flow within the 0 volts to negative 10 volt range of potential differences, but be prepared for students to think their experiment has stopped working. If, however, students do measure a significant current in this direction, then it means they have a faulty diode and it should be replaced.
In describing the main features of a current against potential difference graph for a diode or an LED, students should ensure that they include both negative and positive potential differences. When a negative potential difference is applied across the diode, i.e. it is in reverse bias, the thickness of the depletion region increases. The resistance is very high and no current flows. If a very high potential difference is applied in reverse bias, then eventually the diode will break down and resistance will drop dramatically. This hasn't been shown on this graph. In forward bias, i.e. when a positive potential difference is applied across the diode will start to conduct at a very specific potential difference, for example 0.7 volts. The resistance will become very low and the diode conducts. Interesting part of the graph is when this actually happens. We say that the diode has switched on, and the student may like to go back and take more readings around this value to determine the shape of that curvature as the diode turns on.
Thermistors and light-dependent resistors are unfortunately beyond the scope of this video. Both tend to have high resistances in the order of several hundred ohms or more. As a result, within the normal range of potential differences available in class experiments, the currents would not show up on a normal laboratory ammeter. And just a final reminder, the full versions of the experimental videos that we've used, together with teacher notes and Excel versions of the results and graphs, are available by following the links shown. Thank you very much for watching.